Welcome everyone to another exciting conversation. In today's video, I'm not going to talk about time travel in the way you might think. How do we scientifically travel through time to the past and the future? What are the scientific discoveries and calculations related to time travel? What are the various problems that arise during time travel, the time travel paradoxes, and the conundrums associated with it? Let's discuss all of this and release it as a time travel capsule. Then, we'll explore why we still haven't been able to practically achieve time travel as humans. So, join me in today's video as we dive into all these topics in a very engaging way and embark on a fascinating time journey. Today's program is about time travel. When you hear the term time travel, most people instantly think of traveling to the past, right? But friends, time travel encompasses two branches: traveling to the past, which is backward time travel, and traveling to the future, which is forward time travel. So, when we talk about the topic of time travel, we need to address both these categories, past and future time travel. In fact, at this very moment, the world's top-ranking universities and next-level researchers are relentlessly conducting experiments on this subject. They've produced tons of research outputs based on their studies. Not only that, professors like Ronald Mallett have been tirelessly conducting research on time travel for about a decade. I mention Professor Ronald Mallett here because he's even referred to as the real-world time traveler in some circles. Can you imagine why? Why are these scholars and research institutes spending billions to conduct experiments on time travel? Are they trying to build a time machine to go to the past or future to change something? No, friends. They're trying to understand the differences in nature and reality, how things happen in space-time in a completely different way. That's why time travel is no longer just a sci-fi story. It has become one of the leading research areas in the current scientific research pool. Got it? So let me ask you a series of questions. Do you have answers for these? Have you ever seen time? Or have you ever felt what time is? Have you heard of someone touching time somewhere? Someone might say, "Oh, I see time every day on this clock." Everyone can see time on it. But friends, what's on the clock is the time of day. We're talking about time here. To clarify a bit, a clock is a tool invented by humans to represent time. The time of day is the message conveyed by the clock, right? Now, let's talk about time in a simple way, diving a bit deeper. Sir Isaac Newton, a giant in classical physics and one of its founding fathers, said that time is like an arrow released from a bow. Once the arrow is shot, there's no turning back. Similarly, according to Newton, time doesn't turn back either. It moves forward in a straight, linear path. But friends, according to Albert Einstein, the great genius of the century who opened new dimensions in physics, time doesn't behave the way Newton described. For Einstein, time is like a river, a time river, as the concept is called. Einstein says time flows like a river, with varying speeds, meaning fluctuations in pace, along an uncertain path. According to him, that path could be a straight line, a curved path, or a winding route with bends. It could even be a combination of all these. He also says that just like a river has whirlpools and unpredictable currents, time can have unpredictable changes that we can't foresee. Just as a river can split into multiple branches or have parallel rivers flowing alongside it, time could also split into multiple branches. And there could even be parallel time frames alongside one time framework. That's what Einstein says. Friends, through these concepts, Einstein's theory of relativity unlocked and set free the concept of time travel, which had been locked away and confined by Newtonian mechanics for so long, taking it to a new dimension. Even today, most time travel theories used in research are based on Einstein's theory of relativity. Let's start by discussing both past and future time travel in detail. First, I'll take future time travel, or forward time travel. In the simplest terms, the concept here is traveling through time to the future in some way. Scientists around the world have been working on this for a long time, spending millions of dollars on research. Based on this research, a plethora of scientific concepts, mathematical equations, and models have been developed specifically for forward time travel. Let's talk about a few of the most prominent concepts. One of the main, powerful, yet simple concepts that can be demonstrated through calculations is time dilation. This concept is based on Einstein's special theory of relativity. Time dilation explains that when a person travels at extremely high speeds, close to the speed of light, their aging process slows down compared to someone who is stationary or moving at a much slower speed. But friends, for time to slow down like this, the speed you need to achieve is close to the speed of light, which is 300 million meters per second or 186,000 miles per second. Sounds a bit overwhelming, right? Let's simplify it with a basic calculation. Imagine an astronaut boarding a special spaceship and traveling at 95% of the speed of light for 5 years in space, then returning to Earth at the same speed. For simplicity in our calculations, let's assume the entire journey, 10 years round trip, happens at a uniform 95% of the speed of light. This means there's no deceleration when the astronaut turns around after 5 years. Now, this astronaut is leaving their twin sibling on Earth. One person is stationary on Earth, while the other is traveling through space at 95% of the speed of light. After 10 years in space, the astronaut returns to Earth. But friends, according to time dilation, for the twin who stayed stationary on Earth, those 10 years aren't just 10 years. For them, it is calculated as 32 years. This means, relative to the stationary observer on Earth, the time for the person traveling at 95% of the speed of light passed more slowly. In other words, compared to the sibling on Earth, the astronaut who traveled in space aged more slowly. Theoretically, they've traveled to the future. This is what's called the twin paradox, friends, which Einstein also referred to as a paradox. While this can be beautifully calculated and demonstrated, putting it into practice brings up an endless array of problems. According to Einstein's mass-energy equivalence, E in mc2, as an object approaches the speed of light, its mass increases infinitely. If that object is a time machine, the increasing mass requires more fuel to keep moving. More fuel increases the mass further, creating a vicious cycle. The conclusion here is that with the conventional fuels we use on Earth today, like chemical fuels, achieving time travel is impossible. Friends, at this very moment, time dilation is being experienced by scientists, humans, or even a kitten aboard the International Space Station, ISS. Here's how. The ISS orbits Earth at high speeds. This causes time dilation, where time aboard the ISS passes slightly slower relative to Earth. So, if someone goes to the ISS, stays for a while, and returns to Earth, they've technically traveled a tiny bit into the future. However, this time difference is extremely small. There's another theory where the time difference could be significant: gravitational time dilation. According to this, in an extremely strong gravitational field, like one 100 times stronger than Jupiter's, time passes much slower than in normal conditions. If someone goes to such a place, spends time there, and returns to Earth unharmed, they've theoretically traveled to the future. If you've seen Interstellar, you can visualize this. Remember the scientist who went to that planet and returned to find his young daughter had aged into an elderly woman? That's future time travel. But to achieve such an effect, you'd need a gravitational field as strong as a black hole, and you'd need to survive the journey there and back. Currently, we don't have spacecraft or suits capable of withstanding such extreme gravitational fields. Even the most advanced spacecraft would be crushed in seconds. So this concept remains purely theoretical. Now, let's talk about animals. What if I told you there are creatures that can travel to the future without any issues? Would you believe it? That fascinating species is bears, friends. Bears can naturally do this through hibernation sleep. During winter, they eat, drink, crawl into a cave, and sleep through the entire season. This isn't ordinary sleep. It's a deep hibernation where they skip winter and time travel to spring. While bears can do this naturally, humans don't have this ability. However, hibernation sleep is frequently used in sci-fi movies like Prometheus or Interstellar. In these films, people are placed in special chambers where most bodily functions are slowed down, almost like shutting down the body's processes. During this time, they time travel to the future. But in reality, we haven't found a way to safely halt human bodily functions without damaging cells, tissues, or systems. If we ever find a successful method, it could be used for long-duration space missions. We've discussed several famous scientific theories for future time travel, but none allow us to jump to a specific point in the future instantly. However, there's a concept that could theoretically allow such jumps: the Einstein-Rosen Bridge, or wormhole. In 1935, Einstein and Nathan Rosen, using the theory of relativity, proposed this idea. According to relativity, time and space are interconnected, forming space-time. A wormhole is like a shortcut through space-time, bending it to connect two distant points. To explain practically, imagine space-time as a sheet. You're at one point, the present, and want to travel to another, the future. By bending space-time, you connect these points and create a tunnel, a wormhole. Think of it like an apple. A worm at one side of the apple could crawl across the surface to the other side, covering a long distance. Or it could burrow through the apple, taking a shortcut. That's what a wormhole is, a shortcut through space-time. Using an Einstein-Rosen bridge, you could travel 1,000,000 years into the future or even to the past by creating a stable wormhole. Creating and maintaining a wormhole brings countless challenges. To open a wormhole large enough and keep it stable, you'd need energy far greater than the atomic bomb's explosion. Energy on the scale of a supernova. Even then, maintaining stability is a massive hurdle. As of now, Earth's technology isn't advanced enough to create stable, large-scale wormholes. However, mathematical models suggest it's possible, which is why time travel remains a topic where you have to see it to believe it in the scientific community. While we can't yet send humans through wormholes, scientists have conducted experiments at the atomic and subatomic levels using particle accelerators. They've used antimatter to try stabilizing wormholes, but the amount of antimatter we can produce is insufficient for large-scale applications. Still, researchers are working hard on this. These are signs of what might be possible in the future, right? That's the story of future time travel. Now, let's jump straight to backward time travel, traveling to the past. Before we dive in, think for a moment. Why would a scientist or a billionaire want to travel to the past? For most, it's to do something they couldn't in the past, relive a precious moment, correct a grave mistake, or change critical historical events to make the world a better, more peaceful place. But friends, traveling to the past and the future are not the same. If you travel to the future and change something, it doesn't affect the present because the future hasn't happened yet. But changing something in the past, which has already occurred, could directly or indirectly alter the present and future. This is due to causality, the idea that the present is shaped by past events. Let's talk about the scientific methods for backward time travel. The most powerful and successful theory is the Einstein-Rosen Bridge, which we discussed earlier. Here, you'd connect the present and the past through a wormhole, just as with future travel. But all the challenges I mentioned earlier apply here too. Leading researchers believe there's hope for time travel only through wormholes activated by a time machine. However, renowned physicist Kip Thorne says that turning a wormhole into a time machine could cause a massive explosion, destroying the wormhole, the time machine, and everything around it. He's proven this mathematically, not just conceptually. Thorne argues that to make time travel a reality, we must advance our understanding of quantum gravity far beyond current levels. So, friends, backward time travel, like forward time travel, remains a scientific concept for now. Yet scientists like Dr. Ronald Mallett, who've dedicated their lives to building time machines and developing theories and equations, keep the field alive. Because of this, time travel is a fascinating topic in both scientific and sci-fi communities. If humans ever gain the ability to time travel, it will undoubtedly reshape reality itself. I'm signing off. See you in the past or future.